All right, here we go. 14.6 in your textbook. 11.4, I believe, is where we are at. So if you want to reference in your book, 14.6. We're going to call this just bases. So kind of the opposite you can maybe sometimes think of as acids. Using a little bit different PowerPoint format today. On the left side of the screen, you're going to see sodium hydroxide, which is probably the most common base. This is actually what it looks like. It's white pellets in the solid form, and this is the space-filling model of sodium hydroxide on the left. It's IUPAC name, sodium hydroxide. Systematic name is sodium oxydenide, and their common names, the names that you probably hear on the street, are caustic soda and lye. All of those things refer to the same stuff, sodium hydroxide. So it's a base. Okay, and we have many other bases, but that's probably the most common of all of the bases. All right, so let's just go through our definitions again. You don't have to write this slide down, as you're probably well aware of most of the things on there. Bases, for the most part, via the Arrhenius model, bases produce hydroxide ions in aqueous solution. That's different, obviously different than acids, because acids produce hydrogen ions in aqueous solutions. So bases don't produce hydrogen, they produce hydroxide, according to the Arrhenius model. That doesn't cover all the types of bases that we know of, though. So we needed to come up with some different definitions, and that's where the Bronsted-Lowry definition comes in. It says that bases are proton acceptors. So they're things that will actually absorb the hydrogen ion. Again, that doesn't cover, again, all of the bases, so we go to the Lewis acid model, where bases are electron pair donors, where they give electrons away. So these are the three different types of models that we have to know. The top one is the most common, the Arrhenius model. I would say the Bronsted-Lowry is second most, and the Lewis acid is used the least. So here's just a general dissociation reaction of a strong acid. You've got some type of metal that I'm going to abbreviate, or this PowerPoint abbreviates with a capital M, that bonds to hydroxide, and that's a solid material. And then if we dissolve that into water, all metal hydroxides, by the way, are solids at room temperature. If we dissolve that into some water, we're going to get aqueous metal and aqueous hydroxide. And notice that if we're not at equilibrium, we just have the arrow pointing to the right, because this is going to be such an incredibly high dissociation. There's going to be no remaining metal hydroxide left. So there's really two types of metallic hydroxides. Those are the group 1 hydroxides, lithium, sodium, potassium hydroxide, and they're very soluble. And they're also probably some of the stronger bases that we know of. So they'll easily dissolve into water. The group 2 hydroxides are a little bit less soluble. Calcium, barium, magnesium, strontium hydroxide. Those are less soluble. And the strength of the base, the pH of strong bases, is calculated directly from the concentration of the base in solution. So because group 1 hydroxides are more soluble, that's probably going to give them more hydroxide dissolved into solution, giving them a higher concentration, and thus a higher pH. So now let's take a look at weak bases with water. The weak base itself is going to react with water, producing its conjugate acid and the hydroxide ion. And so we're going to get something that looks like this. Here's methylamine. I had this drawn on the board. This is the stuff that they stole in Breaking Bad, that we combine with water. And if we do this, the methylamine is going to grab onto one of those hydrogen ions and form the CH3NH3 ion. The leftover stuff here is going to be the hydroxide ion. Now, as you can probably imagine, hydroxide is a pretty aggressive base. This guy, let me just write this here, is the conjugate base. Okay, it's very, very aggressive. This is the base, this is the acid, this is the conjugate acid. Okay, it's very aggressive, and it's really, really, really going to want that hydrogen ion from the CH3NH3. So more often than not, it is actually going to win that battle, and it is going to pull that hydrogen back, and it is going to force equilibrium back in that direction. And that's kind of the definition of a weak acid or a weak base. It's just that initial material stays the initial material, doesn't dissociate all that much. And that's reflected in the Kb for this particular base. If you look at how small it is, 4.38 times 10 to the negative fourth, it kind of indicates that the reaction is going to primarily lie to the left. So the stuff on the left, the methylamine and the water, are going to be the primary species in solution, where the stuff on the right is rarely going to exist. So we can write an equilibrium expression with all of this material. We've got the CH3NH3 ion, that is our conjugate acid. We've got the hydroxide ion, that's our conjugate base. And we've got the methylamine on the bottom being our original base. And noting that the original base is pretty weak, so we're going to have a high number down at the bottom. This will be high. Hydroxide will be low. And the conjugate acid will be low. And because of that, we've got a Kb that's relatively low as well. Alright, so here's some Kb's for some common weak bases. I am sure this is in your book somewhere. In fact, it is. It's on page 600. It's not as complete in your book, actually. On page 647, you'll find this table, and it's giving you some Kb's for common weak bases. Note that I'm not giving you Kb's for strong bases, because Kb is undefined for strong bases because of the almost 100% association. There's just this PowerPoint has a little comment down here. Many students struggle with identifying weak bases in their conjugate acids. What patterns do we see that may be helpful? And we talked a little bit about taking a look on the right side of an equation and thinking what the negative ion is going to want to do. Well, the negative ion is going to want to absorb the hydrogen back. And if it's absorbing the hydrogen ion back, it is going to be a proton acceptor, and that defines the conjugate base. So I think the more practice we have with that, the better it's going to be. And I think one thing that really helps is if you kind of just write out a statement. The conjugate acid of this particular reaction is this because of this. So the more of that you do, the better this will be. So here's our generic reaction for a base reacting with water, producing the conjugate base and the acid. So that's what we can kind of write for a generic. We don't have to look at just methylamine. We can look at really any type of amine that we come up with, or any type of Bronsted-Lowry base or Lewis base. Just a short note here. Amine, when you hear that term, amine, usually you want to think of base. And there's a lot of different types of amines. We just saw methylamine. But you also have like dimethylamine and trimethylamine. Those are just nitrogen-containing compounds. I'm going to draw trimethylamine. This is also abbreviated TMA. I used to make this Sigma Aldrich. A little bit explosive. And if you got a little TMA here, trimethylamine, you'll notice that there's this like docking spot right here that seems to be a nice acceptor or receptor for hydrogen. And it is. Once in a while, you'll get a hydrogen ion to kind of lop itself right here. There you go. And so this whole big thing then becomes a positive ion, and it becomes this. Now that trimethylamine becomes that conjugate acid. So, but like I said, it's only once in a while, because if this occurs, then what else is produced? This is produced, OH. And what do you think OH is going to do? OH is going to take a look at this guy. OH is going to get angry, and OH is going to pull this back, thus forcing the reaction in that direction. My goodness, this is a mess of a slide. All right. One important note, all weak bases do this. This is kind of the same stepping stone that they all form, and I could say the same thing for weak acids. So don't overthink this to make it too complicated. All weak bases kind of follow the same equilibrium expression. All right, let's go through an example problem. We want to figure out the pH of a 0.5 molar solution of ammonia. Ammonia is a weak base. NH3, although it is pretty nasty stuff. If you do ever have to work with ammonia, or in solution, it's known as ammonia hydroxide. Well, I suppose those two things are different. If you do have to work with ammonia, it's usually a gas. It's very stinky, so try not to smell it too much. So I'm giving you the Kb. We're going to approach this just like we approached those acid problems. First of all, let's write the equation for the reaction, certainly at equilibrium because it is a weak base. See if you can go ahead and define the conjugate base, conjugate acid. The OH in this case is the conjugate base. Step 2, we're going to ice it. So let's produce an ice table. We know the concentration of the initial ammonia solution. So that's going to give us some information about the first line. Taking a look at the stoichiometry of the particular reaction, we know how we're going to change. And so we should be able to figure out what we're going to be at equilibrium. So through this, we can write our equilibrium expression then. I don't know if I've ever explained this, but the equilibrium expression, sometimes you'll hear it called the law of mass action. This whole idea down here that we always write this thing is called the law of mass action. That's kind of cool, but I don't know if we really need to know that. All right, so we've got our equilibrium expression. We are doing the assumption here. Again, why am I making that assumption? Well, there's your concentration. Okay, that's to the negative first. And there's your KB to the negative fifth. So if you look at the differences in exponents, that's the difference of 4. We said that if the difference is 3, you usually can make the assumption. So this is greater than 3, so we can make the assumption. You know, at the end, if you want to go through the 5% rule to make sure that it is valid, you certainly can do that. All right, so let's solve for x. Remember, x is also the concentration of hydroxide. Guys, at the end, that's what we want to get to. If we know concentration of hydroxide, we can very easily figure out the concentration of hydrogen. And if we can figure out the concentration of hydrogen, then we can easily find out the pH. So we do that. We get a concentration of hydroxide of 3 times 10 to the negative third. Let's convert OH to pH. There's multiple ways to do this. Right now we're just going to take POH. The negative log of the concentration of hydroxide ions is 4.52. Then all you got to do is take 4.52 and subtract it from 14, and that'll actually give you your pH. And that resides at 9.48. So you always, at the end of the day, you want to check your answer, make sure that it's correct. Ammonia is a base. So if you've got this stuff in solution, you should probably assume that you're going to have a pH that's greater than 7. And we do. 9.48 is greater than 7. All right, that's it. Ooh, under 12 minutes.